Assalamualaikum and hi to everyone. Today I'm going to introduce you to my final year project entitled of 3SS Balance Sensor System for Aerodynamic Load Measurement. My name is Amy Shakila binti Adham and my matric number is 193811. I'm doing Bachelor of Aerospace Engineering in University Putra Malaysia. My supervisor for this project is Dr. Muhammad Faisal Abdul Hamid. Before we jump to this topic, I will explain a bit about wind tunnel and aerodynamic components so that you will get an idea what I'm going to talk about. For aviation design specialists, yet in addition for mechanical and civil engineers, wind tunnel are significant device. A standard educational wind tunnel only needs to calculate the lift and drag forces that can be able to monitor the installed model. Aerodynamic component and device are typically evaluated on scale models mounted within a wind tunnel that experimentally predicted the life cell models. Aerodynamic confirmation can be obtained by performing of an expensive and time-consuming wind tunnel test would likely yield results that are more precise than needed. Here is the sketch of the installment device of the force balance in the wind tunnel. However, having precise results with a huge system is not a simple task. Huge system has a complex system, expensive, and many instructions to run the system. The solution for this problem is by constructing a simple, affordable, and understandable system to measure lift, drag, and pitching moment for a small, low-speed wind tunnel. The aim for this project is developing a simple 3-axis force balance system able to measure lift, drag, and pitching moment designed for a small, low-speed wind tunnel. While the objectives are to obtain design specification of 3-axis balance sensor for low-speed wind tunnel force measurement, to design 3-axis balance sensor using multiple load cells and microcontroller for force measurement, and to perform an aerodynamic measurement using the 3-axis balance sensor with a case study thin plate model in the wind tunnel. Moving on to the scope and limitation. The scope of this project will cover the construction and calibration process of the whole structure. The other scope is the data acquisition and processing system can be designed and built, the code needed to read and process the data. This project will be focused on to get to measure only 3 of aerodynamic load for the following reasons. I had done reviewing many literature in aerodynamic field, but I want to focus on 2 different literature that I have reviewed. The first one is by Tim Theoret, where his focus is similar to this project. The aim is to provide an accessible tool to do measurements in the faculty's wind tunnel that now used mostly for demonstration purpose. Next, the paper by Tomin, Scipioni, and Getty that presented a clear step-by-step procedure on how to construct a force balance for educational purpose. The figures below shows the force balance on their projects. Speaking of the methodology, I have 6 main steps involved with start from an analysis of the system specification needs for the wind tunnel use are identified. First, system specification. Second, design and assemble. Third, fabrication. Fourth, electronic system. Fifth, assemble. And the last one is case study testing. The image shows the arrangement of the load cell. This is the design of the force balance structure, which consists of upper platform, vertical bar, horizontal platform, load cell, and support platform. Here is the matrix on how to get the lift, drag, and pitching moment, where F is the force and X is the distance between leading edge and the load cell. To connect the ideas, the picture shows the circuit diagram for force balance system, while at the left-hand side shows the wire connections. Shows here is the construction part, force balance, Arduino connection, and the whole system in the wind tunnel, where the airspeed is from 0 to 10 meter per second with increment of 2, and the angle of attack is from 0 to 10 degree with the increment of 2. In calibration process, I use dead weight to get the reading. The first graph shows for the accuracy of lift and pitching moment reading with the maximum error of 0.6%, while the second graph will show the accuracy of drag reading with the maximum error of 0.9%, where the F1 is the force 1, F2 force 2, F3 force 3, WD dead weight. It will indicate that the data to be obtained in the experiment is accurate. This part shows the outcome of the system. The results are for 2 meter per second airspeed by using thin flat plate. At the left-hand side, there is the comparison graph for CL theory and CL experiment, where it shows the 0.05 difference of gradient between the two graphs. The difference is affected by the increment of angle of attack that increase the vibration on the flat plate. The second graph shows the other component that we can get from the system. The size of thin flat plate will affect the reading of the force. On the other hand, manual adjustment of angle of attack is the possibility of an error. To sum up the project, a 3-axis force balance system that able to measure lift, drag and pitching moment in a small low-speed wind tunnel has been designed, fulfilling the major objective of the thesis. The design has been constructed as simple, affordable and understandable as possible. It is possible to make change to the system in order to improve or include further calculation. That's all from me. Thank you for listening to my elucidation and see you guys in the future.